All right, so let's get started on our first section, 1.1. There's 2 days of it. We'll start with the first one, which is functions. Okay, so first off, we write all of our domains and ranges in interval notation. So interval notation, just as a reminder, is a method of writing down a set of numbers. So there's inequality notation. So if you look at these problems right here, they're all written as inequalities. We write them in interval notation. So you did this in Algebra 2 using brackets and parentheses, okay? So for example, if you had x's in between a and b, it would look like this. Here's a and here's b. So your number's in between those two, and it's closed points because that's greater than or equal to, less than or equal to. It looks like two less than or equal to signs, but it's greater than or equal to a, less than or equal to b. And that says x is in between it, right? So that's how it looks, and then we would write it with a bracket. So bracket, and then you would say where it starts, which is a, where it ends, which is b, bracket, because you're including it. If you're not including the point, because it's an open, then it is an open point, an open circle on your graph, and that's if it's less than or greater than, and not less than or equal to, greater than or equal to. So you'd use a parentheses there. Also, you always use a parentheses on infinity symbols. So it starts at negative infinity, and when I say start, usually I have air quotes holding up in the air, so you can't see me doing that. You have a parentheses on that, and then on the other infinity also. So also, we're going to be using U for union. It's what we use to represent it. So like it looks, I'll trace it right here. It's like this. Some people accidentally do that. It's not like a lowercase u. It's a union symbol, and it's used for the word or. Okay, I'm like stumbling over my words from my first video here, but I'm not going to restart. Okay, so this one says write each inequality in interval notation. So if you can do this without drawing it, great. If you can't, I always tell everyone, if you're getting things wrong, you need to sketch it. Okay, so if I needed to know what this looked like, there's a 2 right here. It's open because it's greater than, not greater than, or equal to, and all values greater than are this direction. So now I'm going to write it as an interval. Okay, so if I'm writing it as an interval, let me switch colors here to make sure we're not confusing it. This is an open point, so I'm going to use a parentheses. So parentheses 2, comma, and then you're going to say where it ends. It ends by going forever, so it doesn't end. So infinity, and then always a parentheses on infinity. All right, here's the next one. I have 3, and it's closed and including, and it's values that are greater than or equal to. So this right here, it starts at 3. You're always looking left to right, so bracket 3, comma, and then it goes forever, infinity. This one right here, we have 4 right here, open point. These are values less than. So now for this one here, remember you're always looking left to right. So air quotes starts right here, right? This is forever. So forever in the negative direction is negative infinity. And then it ends right here at 4. This one right here, 5, closed point, forever in this direction. And then once again, looking left to right, air quote, this is where it starts, this is where it ends. So negative infinity to 5. Okay? If you look at it and you're like, oh, values less than or equal to negative 5. That's negative infinity to 5. No picture is necessary. It's if you need to think through it first. Okay? All right, compound inequalities. So this one right here says x is less than 5 and x is greater than or equal to 2. So I'm going to once again do a sketch here so I can see what I'm working with. So 2's here, 5's here. I'm including 2. I'm not including 5. All right, so this one says x values that are less than 5. So that would be shading in this direction, right? And would go on forever and ever and ever. But it says it also, so and x values greater than or equal to 2. So that's in this direction, right? So it's only values in between those two. So now I want to write this in interval notation. Here's the start. Here's the end. So it's from 2 to 5. This right here says x is in between negative 4 and 7. So this one's probably the easiest one for me to do. It's in between negative 4 and 7. Not including negative 4, not including 7. Last one right here, 2, 8, open, closed. All right, so this says x values Less than 2, so that's this direction. This says x values greater than or equal to 8, so that's this direction. So here you have, they're broken up, right? So you're going to have to write 2 different intervals. So we'll start with this one on the left right here. So this one starts, air quote, here, ends here. So negative infinity to 2, parentheses on both. And then you're going to use the union symbol. And then this one starts at 8, goes forever. So bracket 8 because it's closed forever. Okay, I'm going to try to stop saying air quote, but that's what I would be doing in class. Okay, so that's just how to write it. When we're writing it, most of the time we're talking about domain. Sometimes we're talking about range. We're not going to hit range yet today. So domain is the set of input values for which a function is defined. In other words, the function is able to provide an output for each member of its domain. So if there's an output for that input. So I think of it as all possible x values. So you've done this before. You've written domain of a graph. So if this comes easy to you, great, because it's supposed to. You've done it before. All right, so the first one's 3 pieces, okay, separated by asymptotes. So you're going to do each piece separately. You're going to have 3 different intervals. You're always working left to right. You may not mix them up. So here's this first one. Starts here, ends here. Okay, so it starts at a arrow pointing to the left. So that's negative infinity. And then it continues and it stops at this x value right here. Okay, so that x value that it stops at is negative 1. Union. Now you can look at this piece right here. The easiest way to look at this piece, I would say, is to say, okay, well, it's obviously in between 2 values. What 2 values is it in between? It's in between negative 1 and 2. Union. And then this last piece right here, you can see where it starts and where it ends. It starts at 2 but doesn't include 2 because there's no values at 2 and goes forever. So another way of looking at this graph is that the domain is all real numbers except for negative 1 and 2. And if you look, that's what this says right here. It's saying it goes from negative infinity to positive infinity, but this tells me right here, don't include negative 1. That's the parentheses tell me that. This says don't include positive 2. The parentheses tell me that. So really quickly, something that doesn't make sense if you ever write it down. If I wrote down something like negative infinity to 5, don't include 5, union 5 to infinity including 5. This is contradicting itself. This is saying don't include 5, but include it. So if you're ever in a situation where you see that, that is including 5. There's a value at 5, so it'd just be negative infinity to infinity for this one. Okay? If it looked like this, negative infinity to 5, union 7 to infinity, that's fine because it's all values between 5 and 7 are not included. Okay, this one right here, we're going to see where it starts. It's one piece, and where it ends, it goes from an arrow to an arrow. That means that it goes on forever and ever and ever in both directions. So your domain is all real numbers, and we write that as negative infinity to positive infinity. This one, if you're looking, remember you're always looking left to right for domain, because that's x values. Starts here, or quote, ends here. Can't help myself. All right, so we're going to say where it starts. It starts at negative 3. Oops. Starts at negative 3, and there's a point there, so we're going to close the bracket, comma, and then it goes forever, infinity. So there's domain from a graph. You've done that before. Okay. So the next thing we have to talk about is domain from an equation, right? When you're looking at equations, I have them broken up into 1, 2, 3, 4 different groups, okay? When you're looking for domain, what you need to be doing is you need to ask yourself the question, is there anything x cannot be? Okay, is there anything x cannot be? If the answer is no, x can be anything, then your domain's all real numbers. Okay? So where are there situations where you should be answering, well, x can't be this? Look at all of the examples in number 5. In fact, let's look at 5a. Can I take the square root of any number that I want to and get a real number answer? The answer is no, right? We can't take square roots of negative numbers. So here there are restrictions. x can't be negative numbers. If you look at this one right here, the next group, this group that are all here, these are all fractions right here. So if I look to you and if I said, is there anything x can't be? You would say x can't be 0. So there is a restriction, x can't be 0. If we look down here, there's square roots and denominators. So if there's anything x can't be right here, it can't be negative and it can't be 0. So we're going to go through these individually, but we're going to start with this group right here. Okay? So if you look at this group in example 4 and I ask you, is there anything x can't be? The answer to all of them is no. X can be anything. Okay? Y, let's think about it. Think about how they look as graphs. Okay, this is like the line y equals negative 2.5. It's a horizontal line. What's the domain of a horizontal line if you look left to right? It's all real numbers. Next one, this is a line that looks like this. If you look left to right, all real numbers. Next one, this is a quadratic. It's a parabola, an upward facing parabola, arrow to an arrow, all real numbers. Next one, this is an absolute value function. It looks like a V, all real numbers. Last one, it's a cubic function. Recall a cubic function looks like this, arrow to an arrow, all real numbers. So all of these are all real numbers, but the way we want you to look at it is to say, hey, there's no restrictions. There's no square roots. There's no denominators. If there's no square roots and no denominators, there's no restrictions and your domain is all real numbers. Okay, so let's look at when there are restrictions. So here we said that x has to be positive, right? It can be 0 though. We know the square root of 0 is 0, but it has to be positive. So I'm going to give you this kind of rule to follow. If you see a square root, and there's something underneath it, which there should be, right? That's called your argument. Okay, so this, whatever's underneath here, that's called your argument. Your argument, which is this right here, argument, I don't know if there's an extra E right here, so my bad if there is, English people, has to be greater than or equal to 0, right? Remember, if I'm saying it has to be positive, it can't be negative. That means it can be equal to 0, but it has to be greater than 0. So greater than or equal to 0. So that's your rule right there. Okay, so first one, let's start. Are there any restrictions on the domain? So really what you should be asking yourself is, are there any restrictions? Yes, because there's a square root. So I'm going to say my argument, that's x, has to be greater than or equal to 0. Now remember, we're writing all of our domains in interval notation. So now you're going to convert that to interval notation. So if you know what it looks like in interval notation, just write it right away. If you need to draw a sketch as we start here, that's fine. That's close point there forever. So that would be bracket 0, comma, infinity, parentheses. And there's your domain. All right, looking at the next one, are there any restrictions on your domain? The answer is yes, because there's a square root. So the argument, this part's the argument, x plus 4 has to be greater than or equal to 0. And now you have to solve this for x. So you have x is greater than or equal to negative 4. And now you can write that in interval notation. We're always going to write in interval notation unless otherwise stated. Once again, if you need to do a sketch of what this looks like, negative 4, close point, all values greater than, so bracket, negative 4, comma, parentheses. All right, last one right here. Here's my argument, right? So it has a square root, so there are restrictions. Negative 3x plus 8 has to be greater than or equal to 0. Solve this. So first I'm going to subtract 8 from both sides. Negative 3x is greater than or equal to negative 8. Divide by negative 3. Now remember, when you're working with an inequality and you divide by a negative, you have to flip the inequality symbol. So now I have x is less than or equal to 8/3. You should not be changing this to a decimal. It's no calculator anyways. Just leave it the way it is. So you're going to write that now in interval notation. Now if you need to draw this on a number line to figure out what it looks like, that's fine. Here's 8/3. Close point. All values less than or equal to that. Okay, so it starts, if If you look on the left, going forever, so that's negative infinity, because it's going to the left, right? Stops at 8/3 and includes 8/3. And there's your domain. So before we do that problem, someone usually raises their hand and they always say like, is it always going to be bracket or parentheses a number comma infinity? If you look at C, no, it's not, right? Okay. Next we have, these all are rationals. They're all fractions, right? So we do have restrictions. We know denominators can't be 0, okay? So if you look at a function and there is a denominator, okay? So it doesn't matter what is in the numerator. So if there's a denominator, okay, right here, I don't know why I did that in the same color there. If there's a denominator right here, the denominator can't be 0. Okay, the denominator can't be 0. So it's not x can't be 0, it's the denominator can't be 0. Okay, so I have a denominator, so there's a restriction. The denominator cannot be 0. All right, so now I have to write this in interval notation. Okay, so I think to start with a sketch here of what this looks like is a good idea. So here's 0, and it's not 0, so it's an open point. So it can be anything smaller than 0, and it can be anything bigger than 0. So now I want to write this in interval notation. To write this in interval notation, it's going to be in 2 pieces with the union separating it because it is 2 pieces. So starting on the left, that's negative infinity. It stops at 0, doesn't include 0, union 0 to infinity. All right, next one. Are there any restrictions on this domain? Yes. There's a denominator. Denominators cannot be 0. Solve that equation. 3x cannot be 1. X cannot be 1/3. So this would look exactly like this, except for this would be a 1/3, right? So I'm going to go straight to writing it. X cannot be 1/3 is written as negative infinity to 1/3, parentheses, union, 1/3 to infinity. And there's your answer. Okay, there's your domain. All right. Next one right here. Are there any restrictions? Yes. There's a denominator. X squared minus 9 cannot be 0. Now I need to solve this. I can solve this by square rooting, but first I have to add 9 to both sides. X squared cannot be 9. Squared to solve. Remember, whenever you square to solve, you have to account for the positive and negative solution. So here we get x cannot be positive or negative 3. Okay. So now I want to write this in interval notation. So if you are working side by side with me on notes, which is a good idea, try to write this in interval notation yourself first and then check it with mine. So just to make sure we know what this looks like on a graph, here's negative 3, here's 3. Not negative 3, not 3, but it can be anything less than negative 3. It can be anything in between negative 3 and 3, and it can be anything greater than 3. So when people first start doing this and they don't draw it, they forget this part right here. So don't forget that part. So my answer, or my domain, is negative infinity to negative 3, union. Negative 3 to 3, union. 3 to infinity. So don't forget about these parts in between, because that's what people forget about. All right, last one right here. X squared plus 8x cannot be 0. All right, I need to solve this. I cannot solve this by square rooting because there's an x squared and an x, so I have to try to factor it. Is there a GCF? The answer is yes, it's x. That's x times x plus 8 cannot be 0. So now I can set each factor not equal to 0 and solve. So x can't be 0 and x can't be negative 8. You can think about what this looks like on a number line, or you can jump right into writing your domain in interval notation. Negative 8 is here, 0 is here, open, open, everything less, everything in between, everything more. So negative infinity to negative 8, union, negative 8 to 0, union, 0 to infinity is your domain. Okay? All right, so far what we've done is we said, just to summarize, If you have a square root, there are restrictions. If you have a denominator, there are restrictions. Now, if you look at right here, we have square roots in the denominator, so there's definitely restrictions. Okay? So, let's think about this first. Just look at this one right here. There are restrictions. Can x be 0? No. Right? X can't be 0 because we can't divide by 0. Can x be a negative number? No. So, x can't be 0 and x has to be positive. So realize when I'm saying that, when you have a square root in your denominator, okay, when you have a square root in your denominator, the argument, which is whatever's right here, okay, so I'll circle that so that we make sure we know that what's underneath is the argument. The square root itself is not the argument. The argument cannot be 0, and it has to be greater than 0. Okay, so when I write that, I don't write greater than or equal to 0, but can't be equal to. That's not how we write it. Okay, we don't write greater than 0 and not equal to 0. Okay, because greater than 0 implies not equal to 0. Okay, so the argument has to be greater than 0 on this. Okay, so looking at this problem, are there any restrictions? Yes, there are. There's a square root in the denominator, so the argument has to be greater than 0. So x has to be greater than 0. Write it in interval notation. So if you're going to jump into writing it into interval notation instead of drawing a picture, 0 to infinity. Okay, once again, if you still need to draw as we're working here when we're first starting, you can and look at it that way. All right, this one, once again, there are restrictions. There's a square root in your denominator, so I know that the argument has to be greater than 0. X has to be greater than 3. Writing that in interval notation, 3 to infinity. If you're still drawing, there's no problem with that. Like if you're still like doing a sketch to help you. Okay? Okay, last section here. This is pretty much a review of things that you've already learned in Algebra 2 that you need to know. But I just want to go through it really quickly through you. So it says, by this stage of your math career, you should already know what it means for a relation to be a function. You should be able to determine if a table, a set of ordered pairs, a mapping, a graph represents a function. If you don't feel completely comfortable with this topic, we want you to reread section 1.1 carefully in your book. Okay, so just to get your brain moving right here, like if I drew this, is this a function? The answer is yes, because it passes the vertical line test. If I drew this, is this a function? The answer is no, because it doesn't pass the vertical line test. Okay. Also, we know that all of these, where they go at the beginning, all these in example 4 are functions. They all pass the vertical line test, right? So if you know what it looks like right now, or you can ask yourself, is there anything, you can ask yourself other questions to help you. Okay. So first thing I want to remind you of is function notation. So it says find of f of negative 2. What does it mean when it says find f of negative 2? It means plug in negative 2. So f of negative 2 is equal to 2 times negative 2 squared plus 3 times negative 2. Negative 2 squared is 4. So that's 8 minus 6, which is 2. So f of negative 2 is 2. The second part of the question says, well, where is there a point on the graph? So what point is on the graph because of that? Remember when we plugged in negative 2 for x, we got 2 for y. So this is our point right here. All right, this one says if f of x is 14, what is x? Remember, f of x is just a fancy way of saying y. So it's saying if y is 14, what's x? So now you're going to set your function equal to 14. So I'm going to change this to a 14 and solve that. So I have 14 equals 2x squared plus 3x. And I need to solve this. Make sure you're doing this part like along with me, because this is the type of stuff that you might be saying like, oh, she said it's algebra 2. I already know it. But a lot of you need to brush up on this type of stuff. All right, I need to solve this equation. Can I solve by square rooting? No. So I want to try to solve by factoring, but it has to be equal to 0 in order to do that. So I'm going to subtract 14 from both sides. 0 equals 2x squared plus 3x minus 14. All right, so now I'm going to try to factor it. Remember, the first step in factoring is always to ask yourself, is there a GCF? The answer is yes. They all have a 2 in common. No, they don't. I lied to you. So the answer is no. I got ahead of myself there. So since the answer is no, I'm then going to use my special factoring x to help me factor this. So I'm going to do a times c right here. That's negative 28. B goes down here, which is 3. So I'm looking for two numbers that multiply to give me negative 28 and add to give me 3. 7 and negative 4. All right, now you have to remember to divide by your lead coefficient. So I have to remember to divide by 2. So I'm going to divide by 2, divide by 2. Now I'm going to look to see if either one of these fractions is simplifiable. The first one's not, so that's going to be 2x plus 7. The second one is simplifiable, so I'm going to simplify it to negative 2 over 1, and that's going to be x minus 2. So I have 2x plus 7 times x minus 2. If you look at my my filled in notes key, I factored a different way. It's another method because I thought I'd throw in different methods in case you want to see a different method. But this is the method that I think most people are comfortable with. All right, so now I need to solve for x, so I'm going to set each factor equal to 0 and solve. So I get two solutions, negative 7 halves and 2. What points are on the graph because of this? So I have the x value of negative 7 halves when I plugged in 14 for y. And I have the x value of negative 7 halves. I have the x value of 2 when I plugged in 14 for y. And these are my 2 points. So these are the points, and those are the x values down there. Okay. Next it says find f of negative x. So we have to make sure we know what this means to do. So let's go back here. What did this mean to do? I meant plug in negative 2. So this means plug in negative x. So all that we're going to do is we're going to plug in negative x for x. So f of negative x equals, so every time I see an x here, I'm going to plug in negative x instead. 2 times negative x squared plus 3 times negative x. And now all I have to do is clean it up. Negative x squared, so negative x times negative x is positive x squared. So that's 2x squared. And then 3 times negative x is minus 3x. So this, you can't solve anything. If I'm plugging in a variable, I'm not going to get a number as an answer. All right, this says plug in m plus 1, right? So f of m plus 1 means plug in m plus 1. Once again, you're not going to get a number answer if you're plugging in a variable. So your m is still going to be in your answer. So let me go back to my equation because I keep forgetting what it is. I'm going to plug in m plus 1. F of m plus 1. Okay, so I have 2 times m plus 1 quantity squared plus 3 times m plus 1. All right, so the only thing I have to do here is clean it up. Okay, so I'm going to expand it so that I can condense it. First thing I'm going to expand is that I'm going to expand m plus 1 squared. Remember, orders of operations inside the parentheses. There's nothing to do there. Exponents next. So now I'm going to do m plus 1 times m plus 1. You can do it off to the side, or you can do it within your problem. I'm going to do it off to the side to keep the problem a little cleaner. So first is m squared. Outer is 1m, inner is 1m, so that's 2m. Last is 1. So now I have 2 times m squared plus 2m plus 1 plus, and then I'm going to distribute my 3 right now, so 3m plus 3. Distribute your 2m squared plus 4m plus 2, and then plus 3m plus 3. Last but not least, combine like terms. 2m squared plus 7m plus 6. Okay? So what people accidentally do on the, and I just said 2 plus 3 is 6. So let's make sure I realize that. What people accidentally do on the quiz and on the test is they say, like, do we have to factor that? Do I set each factor equal to 0? This is not an equation. You do not have to solve. Therefore, there's no reason to factor this. Okay? Last but not least, is this a function? You can think of this 2 ways. Yes, because I know what this looks like. it looks like a parabola, passes the vertical line test. Or we know that for any x value we plug in, we're only going to get one y value. There's nothing that I can plug in that's going to say that gives me two different answers. Okay, so yes. All right, that's notes for today. So go ahead and stop this video and go directly to the homework. If you have questions, you can always come and ask me in the Zoom chat, or you can look back by fast forwarding through the notes. I will be posting the answer key to these notes